We are nowhere near as close to being as smart as we think we are. 14 billion years ago, the universe began, and we still don't know what came before that. Our universe is still growing, and in science, there's only one very important question. Why did the Big Bang happen? It's possible that the biggest problem is that people can't see the Big Bang directly, but NASA hasn't given up yet. In fact, the James Webb Space Telescope has taken the first picture of what is thought to be the Big Bang. What kind of power does this camera have? What does this mean for the future of astronomy? Come with us as we look into this device from the future. What exactly, though, might this amazing technology help us understand about the Big Bang? Before we can dive into that, we need to understand how important the Big Bang is. What is it about this event in space that always gets scientists excited and motivated? At this point, the Big Bang theory is the most popular way to explain how the world came to be. In simple words, it says that the whole universe came from a single point with infinite density and heat. Then, this very small point went through an amazing process of growing and shrinking. At first, this growth happened at speeds that are hard to imagine. After 13.7 billion years, it slowed down to a more manageable rate, ultimately leading to the universe we see today, which is still growing. Even though we can't directly see the beginning of the universe because of present technological limitations, most of what we know about the Big Bang comes from using very carefully designed mathematical formulas and models. The James Webb Telescope, on the other hand, has changed everything. Long before James Webb, astronomers were able to find a strong sign of this expansion of the universe through the cosmic microwave background, CMB, effect. Although a lot of astronomers agree with the Big Bang theory, it does have some critics. Different theories are put forward by some theorists, including ideas like eternal inflation and a universe that oscillates. These different points of view show that scientists are still arguing about how the world came to be and what it is made of. More than 13.7 billion years ago, the universe was in a very dense place called a singularity. It was very hot and contained an infinite amount of matter. Following that, there was a huge and sudden growth that sped up the expansion of the universe faster than light. Alan Guss's groundbreaking idea from 1980 was the first to talk about this era of cosmic inflation, which lasted only a few hundredths of a second or 10⁻32 of a second. This idea changed the way we think about the Big Bang for good. Soon after the era of cosmic inflation ended, more common stories about the Big Bang took their place. A process called reheating took place, which suggests that matter and radiation formed the building blocks for everything in the world today. This includes atoms, particles, and the basic building blocks from which galaxies and stars would eventually form. This process of change took place in the very first seconds after the universe began, at a mind-boggling temperature of about 10 billion degrees Fahrenheit. During this time, the universe had a wide range of basic particles, such as neutrons, electrons, and protons. These were the core parts destined to change into the basic building blocks of our world. At this early stage, the universe was like an unseen soup that light couldn't get through because free electrons scattered light around. NASA explained that these free electrons would scatter light, a process similar to how sunshine scatters through clouds and water droplets. But when these free electrons reacted with nuclei, neutral atoms were formed, atoms that had equal amounts of positive and negative electric charges. This important change made it possible for visible light to appear, marking a major turning point. About 380,000 years after the beginning of the Big Bang, the cosmic microwave background, or CMB, appeared, sometimes referred to as the afterglow of the Big Bang. Ralph Alpher and other scientists first proposed this idea in 1948, and nearly 20 years later it was confirmed. On July 12, 2022, Science Pictures showed the Carina Nebula, the 8-burst nebula, Stephan's Quintet, and a galaxy cluster that stretched the light of objects behind it. NASA quietly shared a beautiful picture of Jupiter while also presenting a study of the composition of the exoplanet WASP 96b. A few days later, scientists made an amazing discovery. They found the oldest galaxy they had ever seen, formed 300 million years after the Big Bang. The JWST is farther from Earth than Hubble, which rotates at an altitude of about 570 kilometers above the surface of the Earth. The JWST is positioned at Lagrangian point 2, which is 1.5 million kilometers from Earth, in a place where the Earth and Sun's gravity balance, making it easier for the telescope to stay in place. This location gives people around the world, and NASA, new ways to look at the stars. But what makes James Webb different from Hubble? People often say that the James Webb Space Telescope is the follow-up to the Hubble Space Telescope, but it has some unique features that make it stand out. The JWST looks at longer wavelengths than Hubble, which mostly studies the visible and ultraviolet parts of the electromagnetic spectrum. In particular, it focuses on the infrared band. James Webb was created mainly to learn about the Big Bang, to look for close exoplanets, study the first stars, investigate supermassive black holes, and search for signs of cold dark matter. It is also designed to explore young galaxies and learn more about how galaxies form. Additionally, it can see the birth of stars and look deeper into our solar system, observing Mars, Pluto, the gas giants, and some asteroids and comets. Following a different design from Hubble, the JWST has 18 hexagonal mirrors set up in a honeycomb pattern, with 6.5 meters between them. This is very different from Hubble's 2.4-meter spherical main mirror. This arrangement increases the surface area significantly. Although the JWST has a larger surface area than Hubble, it can gather light 6.25 times better. Thanks to its improved cameras and a 22x 12-meter sunshield, the JWST is the only telescope that can look deeper into the past of the universe. It is designed to be able to see back in time to the very edge of what we can observe in the universe. In this faraway area, objects have a lot of redshift, meaning that infrared telescopes are necessary to see them. The JWST can take pictures of how the world looked about 100 to 250 million years after the Big Bang, when the first stars and galaxies were formed. With its cutting-edge technology, this ambitious telescope hopes to provide new and deeper understandings of how the universe works. Hubble's end came in May 2009 when its last installation, the Wide Field Camera 3, was completed. This upgrade made Hubble much better at looking at things in the infrared range. As the universe expands, light gets stretched to longer wavelengths, meaning that the oldest things can't be seen in ultraviolet or visible light. The WFC-3 made it possible for Hubble to take pictures of light from distant objects, including the galaxy GNZ11, which existed around 400 million years ago, when the universe was only 3% as old as it is now. However, Hubble only found a few objects from this early period, raising questions. Were these few bright galaxies simply due to instrument limitations, or did they actually represent the early stages of galaxy formation? These doubts were cleared up when the James Webb Space Telescope was launched in December 2021. Scientists named the galaxy class Z12, which is about 50 million years older than GNZ11. Further studies by the JWST showed that many galaxies existed much earlier, some as early as 180 million years after the Big Bang. This was a surprising discovery. Jennifer Carteltape, an astronomer at the Rochester Institute of Technology, noted that James Webb could see many galaxies because they were bright enough. Although everyone knew James Webb would provide new information, no one expected such discoveries. Astronomers also didn't expect what they found: galaxies that were much bigger than previously thought. The current model of the universe suggests that matter couldn't settle down to form galaxies and stars in the first few hundred years after the Big Bang. However, the JWST's first observations, like the SMACS 0723 cluster, made people question this assumption. Erica June Nelson, an astronomer at the University of Colorado Boulder, saw large, red disks that looked like massive galaxies actively making stars. These galaxies, which are thought to have existed between 500 million and 700 million years after the Big Bang, challenge current models of the universe. Calculations show that these galaxies have masses at least 10 billion times that of the Sun, and one might even be as heavy as our Milky Way. These new discoveries from the JWST challenge the way we think about the early universe and how galaxies form. What amazing things about the universe will JWST reveal next? The James Webb Space Telescope, JWST, is truly a game-changer in the world of astronomy and space exploration. Its capabilities extend far beyond those of its predecessor, the Hubble Space Telescope, and it promises to provide deeper insights into the origins of the universe and the nature of the cosmos. Unlike Hubble, which primarily observed visible and ultraviolet light, JWST is optimized for infrared observations, allowing it to peer through the dense cosmic dust clouds that often obscure the view of distant objects in space. This ability is especially important when it comes to studying the very early stages of the universe, as the infrared wavelengths can capture light from the first stars and galaxies, which is otherwise inaccessible to optical telescopes. One of the most exciting aspects of the JWST is its ability to look back in time to the very first moments of the universe's existence. The telescope is designed to detect faint infrared radiation that dates back to just a few 100 million years after the Big Bang. By observing this ancient light, astronomers can study the formation of the first galaxies and stars. These observations will offer crucial information about the evolution of the universe and how it transitioned from a hot, dense state into the vast, complex system of galaxies, stars, and planets we observe today. JWST's ability to study distant galaxies is of particular interest to scientists studying the large-scale structure of the universe. The distribution of galaxies, clusters of galaxies, and the gaps between them can tell us much about how the universe evolved over time. By observing these structures at various stages of their development, astronomers can learn how galaxies formed, how they interacted, and how their growth led to the current cosmic landscape. One of the ways JWST accomplishes this is by taking detailed images of galaxies that formed very early in the universe's history. These galaxies are crucial because they help us understand the processes that shaped the first stars and the chemical elements they produced. In addition to observing galaxies, JWST is also capable of studying the behavior of supermassive black holes, which are thought to exist at the centers of most galaxies, including our own Milky Way. These black holes are incredibly powerful and are believed to play a central role in galaxy formation and evolution. Using JWST, astronomers can study how these black holes interact with their surroundings, how they grow over time, and how they influence the formation of stars and galaxies around them. Understanding the properties of supermassive black holes and their role in cosmic evolution is a major area of research, and JWST's infrared capabilities make it an invaluable tool for this task. Another key area where JWST excels is in the study of exoplanets, particularly those that may have conditions suitable for life. By analyzing the atmospheres of exoplanets, scientists can search for signs of habitability, such as the presence of water vapor, oxygen, and other potential biomarkers. JWST's infrared instruments are particularly useful for this task because they can detect the heat signatures of exoplanets and analyze the light passing through their atmospheres. This data can help scientists determine the composition of these planets' atmospheres and assess whether they have the necessary conditions to support life. The discovery of potentially habitable exoplanets is one of the most exciting frontiers in astronomy, and JWST is at the forefront of this search. The technology behind JWST is also noteworthy. The telescope is equipped with a large, segmented mirror made up of 18 hexagonal segments, each 6.5 meters across. This mirror is much larger than Hubble's, which allows JWST to collect more light and observe fainter objects. The mirror is coated with a thin layer of gold to enhance its ability to reflect infrared light, which is essential for the telescope's mission. The sunshield of JWST, which is about the size of a tennis court, is another crucial component of its design. This sunshield protects the telescope from the heat of the sun, allowing it to operate at the extremely low temperatures required for infrared observations. The shield also helps keep the telescope's instruments cold, preventing any interference from the heat generated by the spacecraft itself. Despite its advanced technology, the JWST faced numerous challenges during its development. The telescope's construction spanned several decades, with the initial concept dating back to the 1990s. During this time, the project encountered a series of delays, budget overruns, and technical obstacles, which at times made the mission seem uncertain. However, despite these challenges, the JWST team successfully built and tested the telescope, and it was launched in December 2021. The launch was a historic achievement for NASA and the global scientific community, as it marked the beginning of a new era in space exploration. The deployment of JWST was also a monumental engineering feat unlike Hubble, which was launched fully assembled. JWST had to be folded up and packed into its rocket to fit inside the payload bay. Once in space, the telescope underwent a complex process of unfolding and calibration, which took several weeks to complete. This process was crucial because JWST's mirrors and sunshield had to be precisely positioned and aligned to ensure that the telescope would function properly. Fortunately, the deployment process went smoothly, and the telescope is now fully operational, providing scientists with a wealth of new data. One of the most significant advantages of JWST over Hubble is its location. Hubble orbits the Earth at an altitude of about 570 kilometers, while JWST is positioned much farther out, at the second Lagrange point, L2, which is about 1.5 million kilometers from Earth. This location offers several benefits. It provides a stable environment for observations, reduces the interference of Earth's atmosphere, and allows the telescope to remain in a fixed orientation relative to the Sun and Earth. This strategic positioning also means that JWST is not affected by the Earth's shadow, allowing it to observe the sky constantly without interruption. With its powerful instruments and advanced capabilities, JWST has already begun to revolutionize our understanding of the universe. It has provided unprecedented images of distant galaxies, nebulae, and exoplanets, and it continues to deliver groundbreaking results. As scientists analyze the data from JWST, they are uncovering new insights into the nature of dark matter, the formation of galaxies, the life cycles of stars, and the potential for life beyond Earth. In the coming years, the JWST is expected to make even more exciting discoveries, deepening our understanding of the cosmos and our place within it. The impact of JWST goes beyond just its scientific contributions. It also represents a triumph of human ingenuity and collaboration. The telescope was developed by an international team of scientists, engineers, and astronauts from NASA, the European Space Agency, ESA, and the Canadian Space Agency, CSA. Its successful launch and deployment serve as a testament to the power of global cooperation in advancing our knowledge of the universe. JWST is a reminder of what can be achieved when people work together toward a common goal, pushing the boundaries of what is possible in the quest for knowledge and exploration. Looking ahead, the James Webb Space Telescope will continue to be a vital tool for astronomers around the world. Its contributions to our understanding of the universe are already profound, and as it continues to operate, it will undoubtedly reveal even more secrets about the cosmos. Whether it's unlocking the mysteries of the Big Bang, discovering new exoplanets, or unveiling the formation of galaxies, JWST is poised to be a cornerstone of astronomical research for years to come. The discoveries made by this remarkable telescope will shape the future of space exploration and deepen our understanding of the universe and our place in it.